Welcome back to Non-Equilibrium Thermodynamics. This is class number 9, and today we're going to start a discussion in or about statistical mechanics and the statistical basis for temperature and entropy. Well, entropy first, temperature second. We'll try to understand where some of these common entropy assumptions and functions come from, and yeah, so it should give us some deep insight uh, about thermodynamics. Now, thermodynamics was developed before the statistical basis for thermodynamics. This was developed by Boltzmann and Gibbs in the later part of the 19th century. Thermodynamics has its roots a bit earlier. And some of the ideas of Boltzmann, as I understand them, were not universally widely accepted at first. People didn't really understand what what constituted matter and whether or not the atomic assumption and the molecular assumption of matter was quite right. So, in any case, thermodynamics came first, statistical mechanics came later, and helped fill in some of the gaps in the details that were missing from the thermodynamics. We're going to start off in a very simple way. Now, we're ideally, I'm only devoting 4 lectures to statistical mechanics, so we can only scratch the surface of this whole topic of statistical mechanics. We cannot in any way do it justice. So there's a lot more there. There's a lot more good. There are a lot of good books where you can go to learn more about statistical mechanics. We're simply going to scratch the surface. We're going to talk about the simplest of statistical mechanical systems. And mostly we're going to stick with particles in a box. And to make life very easy for ourselves, we're going to assume that particle systems are non-interacting. And this simply means that there's no potential, well, the potential energy attraction between two particles can be neglected. Now, particles can collide and can exchange and can collide elastically and exchange energy in that way. But there's going to be, we'll assume that these particles are non-interacting in the sense that there's no potential energy between two particles. This makes the counting of states relatively easy for our case. So let's start with the assumption that we have n particles exactly. They're in some sort of box. We'll label this box volume V, although we don't need to know at first what its volume is. We'll see later that we do. We're going to assume that it's isolated from the rest of the universe, that particles can bounce off this box, but otherwise they're going to stay inside of the box. We're going to assume that each particle can be in any one of exactly R energy levels. So the other simplifying assumption that we'll make to start with is that energy levels are quantized. So quantum mechanics tells us that for particles in a box, this is exactly accurate. But we're not going to rely on quantum mechanics too much more beyond this. We're simply going to say there are discrete energy levels out there. We don't care exactly what their values are, and we assume that particles can exist in these energy levels. Now, the fact that they're not interacting means that if one particle is in a certain energy level, that has no bearing on where any other particle might sit. If the particles are interacting, then they will exchange energy with each other. So if a particle is in bin A and another particle is in bin B, that means they're going to interact in some way. But for our simplifying assumptions here, we're going to assume that the fact that one particle is in a certain bin has no bearing on whether or not any of the other particles are in any of the other bins. So this allows us to completely characterize the system through simple numbers. So the n tuple for us of n1, n2 up to nr, each of n is a non-negative integer. So the non-negative integers I label with n sub 0. This means the 0 plus the counting numbers 1, 2, 3. So we could have in a certain bin zero particles. So we want to allow that. So what does this n tuple describe? Well, it's saying that there are n1 particles in energy level 1, n2 particles in energy level 2, and r particles in energy level r. Now, there's a constraint in the number of particles. Particles can't simply appear and vanish in thin air. And so the constraint is that the total number of particles is fixed. That's capital N. And that is exactly equal to the sum of the particles in the various energy states, various energy levels, I should say. So this kind of tuple will completely characterize the system for these particles which are non-interacting. Again, n sub I means the number of particles in energy level I. The internal energy of the particles, how can we calculate that once we know the state of the system or this tuple? Well, for particles in this configuration, we know that there are n1 particles in energy level 1, n2 particles in energy level 2, and so on. Now, each one of the energy levels is a fixed given number. So the energy of level 1 is U1, energy of bin number 2, energy level 2 is U sub 2, and so on. Now, these numbers here are fixed from the start. They don't change. Quantum mechanics will dictate what those discrete energy levels are, and our system is going to go in and fill those levels. But once we have this configuration, we know exactly what the energy is. Now, for a box of particles that are isolated from the universe, we know that the conservation of energy law has to hold. That means particles will only be able to shift from one state to another if the energy is exactly preserved. So the two constraints in the system become very important for us. This is the constraint for conservation of mass, and this is the constraint for conservation of energy. So we imagine that particles can shift from one configuration to another, but they have to do so within these constraints. They have to satisfy this constraint of mass and this constraint of energy. So we're going to give this, because we use this tuple over and over again, we're just going to give a name. We're going to call it the nu vector. Nu vector. Nu vector is n1, n2, up to nr. And again, it's a r tuple from this space. So each entry has to be a non-negative integer, 0 plus the counting numbers. Now, we said that this completely characterizes the configuration or the state of our system. We're going to give that a name. We're going to call that a macro state. Okay? And we're going to see within macro states there can be a large number potentially of micro states. So a macro state is some way of characterizing the state of the system without knowing the microscopic details of the system. But there can be these things called microstates, which gives the exact microscopic details, if you will, of the state from the statistical mechanical perspective. So I think you'll be able to see how we distinguish these things called macrostates and microstates through a couple of examples, which I'll give you momentarily. So if you tell me what macrostate you're interested in, what you're looking for, I can tell you from combinatorics, if you give me n particles, what are the number of ways that n distinguishable particles can be arranged into that macrostate. Okay, from combinatorics, if you tell me what macrostate you're looking for and you tell me how many particles there are, I can tell you how many ways n distinguishable particles. So by distinguishable, we just pretend like there's a little label on each particle, but otherwise the particles are the same types of particles, like, for example, argon atoms or oxygen atoms, something like this. So this formula is given to us precisely as this. So omega of nu, if you tell me the macro state, I can tell you the number of ways that particles can arrange themselves into that macro state. That's going to actually be the number of microstates within the macro state. And again, I'm going to give you an example which shows this definition. So this is kind of the number of microstates. It's the number of microscopic configurations that give rise to the same macro state. Okay, so let's give an example. Actually, what you need are the next example and the example after that put in tandem with each other to understand what's going on here. But suppose that we have three energy levels. So this is pretty basic. Um, we usually call the energy level that is in position one, we call that the well, what do we call that? The blanking on the definition here. The it's gonna come back to me later. We'll come back to that. The lowest energy state, and then two energy states above that. So just three energy states and four particles. Okay, so how many ways can these four distinguishable particles be put into various macro states? Well, first you have to tell me the macro states you're looking for, and then I can tell you how many ways this can be done. Now, I should tell you, and especially if you know combinatorics, that what we're interested in here is just the arrangement into the macro states. But once particles get into, let's say, bin number one, we don't care what their arrangements are within that bin. Okay? So the arrangement of particles inside of individual bins is not important to us for the counting, only the arrangements into the specific bins to begin with. So how many ways can we take our four particles and arrange them such that all four particles are in energy level one, and none are in energy level two, and none are in energy level three? Well, there's exactly one way to do that, one and only one way. And likewise, if we want to put all of our particles in energy level two and none in energy levels one or three, there's only one way to do that. And likewise, if all the particles go into the highest energy level three, there's only one way to do that. Now things get a little more interesting when we specify the next few microstates, 4 through 9. Suppose we want three particles in energy bin 1 and only one particle in energy level 2 and no particles in energy level 3. There are exactly four ways to do this. And this one's an easy counting problem because really all that matters is how we choose the one particle to go in energy level 2, and there are exactly four ways to choose that particle, all the rest being in energy level 1. All the rest of the macro states in this category are exactly like that. You specify which bin gets the three particles and which bin gets one particle, and then you decide how to choose that one particle to go in energy level 2. And there are four ways to do that, for example. What about if we want two particles exactly to be in energy level 1 and two in energy level 2 and none in energy level 3? Well, it turns out there are six ways of doing that, and so on for these cases. I'm going to give an example of this last one here. And specifically, we're going to count the number, we're going to go through and exactly count the number of microstates in this macro state. There should be exactly 12 ways of arranging particles in this configuration here, and that gives us the number of microstates in this macro state. Now, what I've listed on this side here, okay, in this column here, are all the macro states that I can think of in the configuration. Over here is the number of ways that I can arrange particles into that macro state. So that gives me the number of what are called microstates within the macro state. Now there are three configurations which have the most number of microstates within them, and that's configurations 13, 14, and 15, these last three. So that's going to be very important for us because in statistical mechanics, we're going to be looking for those states which have the largest number of microstates in them. In this case, there's no unique state which has that. Amongst all of these, there are three which have the largest number, 12. And so these will be of interest for us, and I'll tell you why momentarily. Now, as I said, there are a bunch of different macro states that one can imagine in this configuration. In fact, there are exactly 15 different macro states. Now, not every macro state has the same energy levels. Okay. We know how to calculate the energy levels once you give me the macro state, or sorry, the energy level is a fix. We know how to compute the total energy once we know the configuration or the macro state. It's just given by this formula here. So it's not clear because I haven't stated what are the energy levels, whether or not some of these macro states, for example, maybe these six here have the same energy as these three here. It's not clear. Okay, but certainly all the microstates in a certain macro state have to have exactly the same energy. I'll show you how this works with an example. But before we get on to that, let's count the total number of microstates altogether, no matter how many macrostates there are. Okay, so there are 15 total different macrostates. We don't know what the energy level or what the energy values are for them because I didn't give you the energy levels. That information is a separate piece of information. But we do know that there are 15 total macrostates. How many microstates are there? Well, to get that number, you simply sum all the numbers in this column here. Just sum all the numbers that you can find in that column. Well, um, there are three macrostates that have one microstate each. There are six macrostates that have four microstates each. Did I get that right? I got that wrong. So there are three macrostates with one mic microstate in each. That's right. There are six with four microstates. That's this six here. There are three macrostates with six microstates in each. And there are three macrostates with 12 microstates in each. If I sum those numbers up, I get 81. This is 3 to the power 4. And in fact, for these cases, we always have this generic number, same generic number of microstates. If you want the number of total microstates in a system, that's going to be the number of energy levels R, get my pointer back, R, raised to the power n, where n is the number of particles. So this number gets very large very quickly as the number of particles gets larger. So you can think of very simple systems that may only have a few energy state or energy levels in them. Quantum mechanical systems are of this type. There can be quantum mechanical systems where there's only like 10, 15 energy levels in total, but there might be a very large number of particles, like 10 to the 23 or more particles. So this number gets very large very fast. And we're not going to be able to use counting techniques as the number of particles and the number of energy levels rises. But we're going to get back to that problem momentarily. Let's look at this macro state right here. Let's convince ourselves that there are exactly 12 different microstates within that one macro state. So let's examine that one in particular. There's the macro state. One particle in energy level 1, two particles in energy level 2, and one particle in energy level 3. And we want to show that there are 12 distinct ways of arranging four particles, and therefore 12 distinct microstates for this macro state. Now we're going to assume that the particles are distinguishable in some way, but otherwise they're identical. Let's suppose, for example, we have all atoms of the same type. Let's say argon atoms, for example. And we're going to distinguish them by imagining there are little tags or little labels on each one of these four particles. So how can I take these four particles and arrange them such that there is one particle in energy level 1? We're going to call that the U1 bin, 2 in energy level 2, or the U2 bin, and 1 in the U3 bin. So I've listed them out here. And so however you do this, however you want to convince yourselves that this counting problem works is fine. What I've done is I've first fixed the particle that's in energy level 1. And in this case, I've said, okay, well, suppose I fix the particle in energy bin U1 to be particle 1. Then how many ways can I put the other particles in the bin U2 and U3? Well, the first way I can do this is to put 2 and 3 in the second bin, and that would leave the fourth particle to go in bin 3. So notice that this has exactly one particle in bin 1, 2 in bin 2, and 1 in bin 3. And so you can continue this. Suppose that, again, 1 is in U1. Another arrangement would be to have 2 and 4 in bin 2, and then that would mean that bin 3 would have to contain particle 3. And if I have 3 and 4 in bin 2, then the only way to do this is to have particle 2 in bin 3. The next grouping you can do is the grouping where I have particle 2 in bin 1, and then particle 3 and particle 4. And you'll see that every way I do this, okay, of putting a particle in the first bin, that's exactly 4 ways of doing that. And amongst those 4 ways, each one has 3 ways of arranging the other particles. So 4 times 3 gives 12. Of course, that's just a confirmation of the formula that one knows from combinatorics, and we're not going to go any further into that. We're simply going to state that and use it. Now, each microstate in the macro state, 1, 2, 1, has exactly the same energy. This is an important feature. So each microstate in this macro state, there's 12 different microstates. Each one of these represents an individual microstate within this macro state. Each one has to have exactly the same energy level because energy levels the energy value is counted simply through this formula. We're going to sum from I equals 1 up to the number of energy levels, 3 in this case, and then we take the number of particles in energy level 1 times the energy value or energy level in bin 1 plus the number of particles in bin 2 times the energy of bin 2, and the same with bin 3. You multiply those numbers out and add them up. And now we don't have a finite definitive answer of what is the energy for this state because I haven't specified what the energy level values are. But suppose that I take them to be 1, 4, and 5, then I can calculate a specific energy. Now I'm going to get the cart a little bit ahead of the horse here. We now know or have this concept for macrostate. We now know that there can be a lot of microstates in any macrostate. We're going to give Boltzmann's definition of entropy for this, and we're going to argue why this is the right definition of entropy, but it's going to take a couple of steps. So let's get the definition, the cart ahead of the horse, which is the explanation. So the Boltzmann, or the counting entropy of a macrostate. Now, we can only and will only define the entropy for the whole macrostate. Okay, so the Boltzmann entropy of a macrostate is precisely equal to a constant. Now, the constant called Boltzmann's constant is just to fix the temperature scale. We're allowed to adjust this constant, and if we do, we adjust the values of the temperature scale, but only up to a multiplicative constant. So to get the right one for the Kelvin scale or the Celsius scale, we need to take a very specific definition of the Boltzmann constant, and it turns out that that is the one given here. However, if you wish to use a different energy scale, you can change the value of this constant, and your physics, the physics that you do, will be fine. It'll just give us another value in your temperature scale for the freezing point of water and for the boiling point of water, okay? But otherwise, it'll be a nice linear scale, and it'll work out perfectly. So what is the definition? It's the log of the number of ways or the number of microstates in that macrostate, okay? So the entropy, the Boltzmann entropy of a macrostate is some free constant. It has to be positive, but otherwise we can choose it to be whatever we want. the log of the number of microstates within the macrostate. I'm going to argue why this is the right sort of definition for the entropy, and hopefully I do a good job of it. That's coming now. Okay, so why is it important to have this as our definition for entropy? Well, it's based on what's called an ergodic assumption. And for our purposes, we're going to dumb down the ergodic assumption a little bit. We only need a working definition that's given here. Suppose that I have a system of n particles. They're distinguishable because they have labels on them. And we have a definite energy budget, total energy budget of U. There are R levels, energy bins, R different energy bins. And the system of these particles is called ergodic if and only if the system is deterministic. That means it moves from one state to another in a very determined, predetermined fashion. Okay. And I will show you what I mean by this momentarily. Now, what does it mean to move from one state to another? Is it macrostate or is it microstate? It's the microstate. How the system moves from one microstate to the next microstate is entirely deterministic. So that if I know that I'm in a certain microstate to start with, I'm always going to go to a determined next microstate after that. That's what we mean by determinism. The time spent in each microstate, which will give the name the transition time, is always going to be exactly the same, and it's going to be some fixed small number, tau. Now, in the classical Newtonian world, this isn't how things work. There's a continuum of energies, and there's a continuum of the transition from microstate to microstate. In fact, the transition time is exactly equal to zero because things transition continuously. But in our discrete world, we can imagine discrete energy levels and discrete amounts of time spent in each one of the microstates. At least that's going to be our simplifying assumption for this case. The way that things transition from microstate to microstate is deterministic, but it's also cyclical. So once it gets to the end, it comes back to the same transitioning pattern. So I'll show you through an example what we mean by cyclical here in a moment. Each microstate is visited once and only once per cycle through this deterministic cycle. So what do I mean by ergodic? But there's the kind of rigorous definition, or at least a working definition that is good enough for our purposes. But an example is going to go a long way to showing you what's going on here. So what does this mean? Well, suppose that for a certain number of particles, there are exactly 10 microstates, with exactly the same energy. So for our purposes here, we only care about the number of microstates. And here we're working with a system where there's very few number of microstates. That's fine for us. The important thing is that they have to have exactly the same energy, because the only way that you can transition from one microstate to another is if that microstate has the same energy budget as you, because we have this whole idea of conservation of energy. If I'm a group of particles and I'm in a certain microstate, I'm allowed to move to another microstate as long as it has exactly the same amount of energy. This is our conservation of energy assumption. I spend tau seconds in this one, then I transition to this guy, this microstate here. I spend tau seconds in that one, or tau nanoseconds, whatever you like, whatever scale you want. Exactly the same amount of transition time in each one before I move on to the next microstate. Each microstate having exactly the same value of energy, the same energy budget. Of course, from 3, I always move deterministically to 4th state. From the 4th state, I move to the 5th and 6th and 7th and 8th and so on. I have 10 total microstates in this imaginary little system. It's cyclical in that once I get to the 10th one, I'm going to go back to the 1st, okay? And then I go deterministically from the 1st to the 2nd, etc. So this is our simple little ergodic system, going through one microstate to the next. So if I go back to this system here, where I had 81 microstates. Let's suppose that just for the sake of argument, that each one of these macrostates had exactly the same energy budget. Okay, they won't in general. Only a small subset is going to have exactly the same amount of energy. But for the sake of argument, let's just suppose that they all have the same amount of energy. Then there are a total of 81 different microstates. So that's the number of microstates in our deterministic system. Each one gets visited exactly once. So if I was to examine such a microstate or deterministic system, which macrostate would I find? And I just picked a microstate out from random. Which one would I most often find the system to be in? Well, the one that you would most often find the system to be in if you picked at a random time would be one of these guys because they have the most number of macrostates in their microstate. Sorry, I said that wrong. They have the largest number of microstates in their macrostate. So if I'm looking for the macrostate, which is the most probable, okay, if I pick at random, those macrostates that are most probable, if I pick the system at random, it's going to be those with the largest number of microstates. Because remember, systems visit each microstate exactly once in a cycle. The cycle is deterministic. So the macrostate that has the most number of microstates is going to represent a kind of equilibrium. Okay, so our deterministic assumption, before I move on, means that the sequence of microstates is always the same. Cyclical means that it returns from the last one back to the first one, although that's kind of an arbitrary designation. So an ergodic system spends most of the time, okay, if I want to think about it being a system in certain macrostates, then it spends most of its time in the macrostate with the largest number of microstates. Now let's go back to our, well, let me get to this definition and then we'll revisit our definition of the entropy. Of all the macrostates with the same total energy U, okay, and of course I forgot to say it here, but the same number of particles, that kind of goes without saying. Then the one with the largest number of microstates is called the equilibrium macrostate, or just the equilibrium. Now, in real systems, as I start scaling these values up, the number of energy levels and the number of particles in the system, then I haven't graphed it here, but what you'll find is that there emerges one macrostate which has a tremendously much larger number of microstates in them than all the rest. Okay, that's not shown here through this example, but what I suggest you do is go off and do another example where you do exactly the same calculations, but raise the values of this by 1 or by 2. Of course, you're going to start getting into pretty large numbers for the total number of macrostates and the total number of microstates. But there starts to emerge one macrostate which has much larger number of microstates than all the rest. This is the one that we're going to label as the equilibrium. The reason is because in a deterministic system, in an ergodic system, this is the one with the most microstates. This is going to be what is seen most often. So if I imagine a bunch of particles in a box or in a room, then I can imagine, well, there's a few number of ways that I can have those particles be all up in one corner, okay, close together. But there are a much larger number of ways of having things randomly scattered throughout the system. We're going to revisit this analogy later. And so this is why the equilibrium is the one where the particles are kind of evenly and randomly distributed within the system, because it represents a macrostate with a very large number of microstates in it. So again, of all the macrostates with the same total energy, and of course I forgot to say the same number of particles, the one with the largest number of microstates is called the equilibrium macrostate, or just the equilibrium, because that's what we expect to find most often when we look at a system randomly. Okay, you wouldn't imagine these sort of rare events to happen very often in a system of particles. And so a rare event certainly wouldn't represent the equilibrium. But one of these states that has a large number of kind of randomly accessible microstates, kind of evenly distributed, is going to be the equilibrium because it has a very large number of microstates in it. Now, since the entropy is an increasing function of the number of microstates, then the Boltzmann entropy is the maximum or is a maximum for the equilibrium macrostate. Okay, so again, the Boltzmann entropy or the log function is an increasing function of the number of microstates. So if I look for the one macrostate that has the largest number of microstates, that's going to be represented in the Boltzmann entropy as a maximum. So we maximize entropy to find the equilibrium. Okay. Maximize entropy to find the equilibrium. And the reason why is because the log is an increasing function of this. So we're looking for that state which has the largest number of microstates. So why not look for the log of that state? Well, I could use any other increasing function and maximize that. Why not use the square root function, for example? Why not simply take the square root of that? That's also an increasing function. Well, the log is special because there's one other thing we want about the entropy that we want to maintain. Okay, so why do I use the log? Well, suppose I have two identical boxes of particles, or maybe similar boxes of particles. They have the same number of states and same energy budget. What's going to be the entropy of this system? Well, if system alpha over here has, and we're looking at one particular macrostate, if it has omega alpha microstates, and system beta in a configuration, same configuration, has omega sub beta microstates, then the combined system in combinatorics, if we have this number of ways to make the state in this side and this number of ways to make a state in this side, then if I combine the two systems together, the way or the number of ways of making arrangements multiplies. Okay, so this is a fact about combinatorics that the states multiply, or the number of microstates in each system is multiplicative. But this is not what we want for the entropy. We don't want the entropy to be multiplicative as I increase the size of states. We want it to be additive. And the log function nicely allows us to turn things which are multiplicative into things which are additive. And so that's the beauty of using the log. So we've argued the macrostate which represents the equilibrium should be the one with the largest number of microstates. That tells us that we've got to maximize that function omega, right? What did we call that? Omega of nu. But we argued we want the entropy to coincide with the equilibrium. So we want to pick an increasing function of this to represent the entropy, but we want the entropy to be additive. We saw this in thermodynamics. And there are reasons why we want it to be additive from the statistical basis, which we're not going to go into because we're limited in how much time we have. But we want the entropy, when we maximize it, to represent the equilibrium state, but we want that to be an additive function. How do we do that? Well, we're going to use the log because the log breaks multiplications into additions. So the Boltzmann entropy is therefore additive. That is, it's an extensive property of the system, just like the energy is. Okay, you want the entropy to be additive or extensive, like you want the energy to be additive or extensive for a system. And so this says if you're using the Boltzmann definition or the Boltzmann counting method for figuring entropy, then really what you want to do is take the log of this. Now, it doesn't have to be the natural log. One could take log base 10 or log base whatever. So the natural log is nice because it's the natural logarithm. It has some nice properties associated to it. But we could use log base anything else. And in fact, in information theory, they use log base 2 because the standard units there are bits, okay? 0, 1, or 1 and 2, however you want to look at it. And so log base 2 works best for them. So I want to now, we said that things get awfully complicated from the combinatorial setting if I have a large number of particles, and this is entirely true. So we want to transition from the Boltzmann entropy to something which is similar to it or almost the same as that. And the what we want to do is use what's called Stirling's approximation to kind of soften the edges of the Boltzmann entropy. So you may have seen this approximation before. If you haven't, don't worry too much about it. And so the approximation called Stirling's approximation is given in a couple of different ways. We're going to use the logarithmic version because the stuff that we encounter is logs of stuff. And usually it's to replace a factorial with some other function. We're going to replace the log of the factorial. And that's because we're going to be using logs of factorial again and again. And a good approximation for the log of the factorial is n log n minus n. This function comes up a lot in thermodynamics and statistical mechanics. So this is sometimes called the ideal gas function. Okay, n log n minus n or x log x minus x comes up again and again. It's called the ideal gas model, ideal gas function, whatever. So this is Stirling's approximation. Let's now look at Boltzmann's version of the entropy and see what happens if we apply Stirling's approximation to our factorials. Well, if we use the definition of that counting function and then take the log of that, what we get is log, remember it's n factorial over a bunch of factorials. What we get is log of n factorial minus the sum I equals 1 to r of log of ni factorial, okay, in a sum. So what I want to do is I want to replace this log of the factorial and this log of factorial using Stirling's approximation. So there's two approximations made there then. The first one is the approximation made here, and the second one is right there. If I collect terms, I'm going to let you do the algebra offline. What I get is minus the sum I equals 1 to n, I equals, sorry, 1 to r, ni log ni over n. This is nice here because, well, the number is kind of already unitless, but if I divide that unit of number by another unit of number, that gives me a unitless quantity. We're going to see again and again that we want to make sure that the argument of the log is always a unitless quantity. It is here by default, but it's nice to see this pattern because we're going to repeat it from time to time, or actually a few times, I would say. So what is the result of our approximation? In the Boltzmann definition of the entropy, it's log of the number of microstates in the macrostate nu, and we've transformed that to be this sum where there's no factorial functions at all. Okay, now this becomes a better and better approximation as each ni approaches infinity, or the number of particles in each state gets larger and larger. This is a sort of situation that we're looking at. We're looking at large numbers of particles, and so this approximation actually is a pretty good one. So we can replace the Boltzmann entropy with this summation. Now, you might look at this guy here, and we're going to come back to this later as well. Ni over n. Okay, I'm going to give that a name, pi. Pi is ni over n. What properties does pi hold? Well, pi is a positive number, well, non-negative number. This could be 0 on top, divided by its total. If I sum that up, that gives 1. And of course, this looks a lot like a probability, right? What kind of probability is it? Well, if I'm in a certain macro state, For example, if I have n equals 4 particles, 3 levels, and if I consider this macro state, then I can calculate these 3 probabilities from this. How do I get those? Well, I have 4 total particles. And if I calculate P1, that's N1 over capital N4. That's going to be a half. And so the second probability is going to be 1/4. And the third probability is 1/4. So what probability distribution did I just create here? Well, if I have this macro state and I pick a microstate at random, or let's say I pick a particle at random out of any one of the macro or microstates that I have, what's the probability that it's going to be in bin number 1? Well, the probability is going to be a half. What's the probability that a particle chosen at random is going to be in energy level 2? Well, a quarter, and energy level 3 is probability of quarter. So this does represent a particular probability function for us. The question is it all that useful? Well, we're going to come back to that later. And its utility is kind of interesting. We'll come back to that when we talk about the ideal gas law. Now, let's state for our statistical mechanical purposes now what we mean by equilibrium in terms of a postulate. So instead of using, because we're going to be using very large numbers of particles, we want to stop using the Boltzmann entropy and start using what's called the Gibbs entropy. The Gibbs entropy was this transitioned or transformed entropy here. Okay, so we're going to stop using Boltzmann and start using Gibbs. So Gibbs was an American scientist who furthered Boltzmann's work after he tragically died early. And this entropy is named in honor of him. For an isolated physical system of n particles with a fixed total internal energy U, equilibrium is that macro state among all macrostates with internal energy U that maximizes the Gibbs entropy. And there's the Gibbs entropy. Why is it the Gibbs entropy? Well, we're looking for the macrostate which has the most number of microstates. And we argued that, well, to do that, you should maximize the Boltzmann entropy, but the Boltzmann entropy is a little bit hard to deal with when you have large numbers of particles, and the Gibbs entropy is a good approximation of it, and it is easy to deal with when you have large numbers of particles. And so it's going to be the Gibbs entropy that we're going to maximize. So that's going to be the postulate for us from a statistical mechanical point of view, at least for non-interacting particles, for finding the equilibrium. We could equally well look for the maximum of the average Gibbs energy. The average Gibbs energy is just taking the Gibbs entropy, not energy, and dividing by capital N. If I divide this by capital N, the only natural place to put it is as the divisor of this guy. And well, that just gives us the probability in 2 places. So another definition of the Gibbs entropy is through this, but this is what I would call the average Gibbs entropy. So this is, what is it? It's minus a constant. Again, the minus sign is because we've chosen to use the log. The entropy is still itself going to be a positive number. That's because we're taking the log of a fraction, which is always less than 1. Okay, and so for the average Gibbs entropy, it's a sum I equals 1 to r of the probability for the ith state times the log of the probability. So you've probably seen this function appear in, if you've taken statistics before. And again, it has its roots here in statistical mechanics. So we've now defined a postulate to characterize equilibrium. That is which is a reasonable one, I think. We're going to look for a maximum in the Gibbs entropy amongst all states where the energy is fixed and the number of particles is fixed. The question is, can we characterize that that state in some way, quantify it? And the answer is yes. And Theorem 9.9 answers that question in a quantitative way. Suppose that R and N are fixed, so we have a number of particles is fixed and the number of energy levels is fixed. Remember, the values of the energies are always fixed. U1, U2, those are always fixed and dictated by the system. We won't imagine those changing, but the number of particles could change. You could let more particles into the system or you could take a few out. The other thing you could control is the energy budget. So this is the total energy U. But we're going to assume for our system in a box, something I think that is reasonable. The number of particles is fixed. This is conservation of mass. And the energy, the total energy is fixed. This is conservation of energy. So suppose those constraints hold, 9.7 and 9.8. The macro state, nu, that maximizes the Gibbs entropy 9.5. So let's go back up to the Gibbs entropy 9.5. Right there it is. And how did we get there? We started with the Boltzmann entropy. We used Stirling's approximation. If you've never seen Stirling's approximation, please do go through that calculation I just showed. And you get this thing called the Gibbs entropy, which is easier to work with when the number of particles becomes large. The macro state that maximizes the Gibbs entropy 9.5 actually has a nice analytical expression. Okay, we're going to call that the equilibrium state. Okay, and the equilibrium state is characterized by R numbers. The jth number for the equilibrium state, for the equilibrium macro state, has a formula, and it is given as the exponential function minus beta uj divided by the Boltzmann constant times the total number of particles divided by z function, or what we're going to call the partition function, z or z. Okay, here in the States usually z. This is called the partition function. The partition function is a unitless number. Okay, once I fix the energy levels and beta and K Boltzmann, then of course this has to be, because we're taking the exponential of something, this has to be in terms of units, unitless, so that when I take the exponential function, I also have a unitless number. And the units out in front are, of course, 1. There's no pre-factor there. So the partition function is itself a unitless function. This has units of simply number, the number of particles in the state. So essentially that's unitless too, but sometimes you like to think about that as being the unit of number. All right, so the equilibrium is characterized by that, okay, where beta is a positive unique number that's going to be determined. It's kind of a mystery number, but to give away the mystery, beta is going to be exactly equal to 1 over the temperature. So it's going to be related to the temperature. And where does beta come from? It comes from a Lagrange multiplier, a constraint, which we're going to see in a second. So we want to maximize the entropy. If I multiply by a -1, I can minimize the negative of the entropy. So that's what we're going to do, just to make calculations a little bit more simple. I'm going to minimize this function, which is minus the entropy. Okay, I'm not sure why I put K Boltzmann inside here, but I did. Okay, that's fine. Subject to 2 constraints, and the way I'm going to take care of the constraints is the way we've done this before. We're going to use Lagrange multipliers to take care of those 2 constraints. There's the mass constraint, that's conservation of mass, and here's the energy constraint, conservation of energy. So I'm using minus the entropy, because usually entropy has a minus sign here. If I take a minus of a minus, I get a plus. So I'm going to minimize this function j, okay, and it already has the 2 constraints built into it. So let's find the minimum of j. How do we do this? Well, this is a function of r variables plus 2. Okay, r numbers plus 2 constraints, alpha and beta. And the way we're going to do this problem is we're going to use calculus and pretend like n is a continuous number, not a discrete number. Okay, and that has to do with the fact that we're assuming that we have potentially very large numbers of particles involved in our approximation. So n can be treated as a continuous number, just the way we've done already in thermodynamics. All right, so what we're going to do then is take the r plus 1 derivatives of this, partial derivatives, and set those equal to 0, and then hope that that gives us a minimizer. Well, there's some mathematics that has to be satisfied in the background. For example, we need to maybe be able to assume that this function is a convex function, right? In order to prove that it has a unique minimum. Stuff like that that I'm going to brush under the rug because we're going this sort of middle road with our mathematics. So we're just going to take time, or not time derivatives, but the derivatives respectively, and set those equal to zero. Well, we've got our derivatives associated with the numbers of particles in each of the R states, and then we've got the two derivatives associated to alpha and beta. So here's the R derivatives associated to derivatives with respect to nj, set equal to zero. Okay, if you take that derivative, you're going to get a contribution from here, and then simple contributions from here and here. Okay, so this derivative should just give us k Boltzmann log ni over n plus k Boltzmann, the second part here, ni n over ni, 1 over n. You get a bunch of cancellation of terms here, so it's just going to leave the k Boltzmann. The alpha is just coming from this term here, and the beta is just coming from this term here. Well, beta times uj is just coming from that term there. These terms here are just constants, so they fall away. Okay, let's see. Now I'm going to take the derivatives with respect to alpha and beta. What happens in that case? Well, I'm just left with this term, sum equal to zero. So that's just the mass constraint. And the derivative with respect to beta set equal to zero just gives me the energy constraint. So those are just built into the system. The two constraints are the last two equations that I solve when I do my minimizer. This equation here is the one that has the meat in it. And so if I saw, what do I want to do to find the values of n, ni, or nj? I guess I did that wrong, right? So this should be ni. It'll come back. There we go. Okay, I used ni. And I need to use I there as well. Looks like I wanted to switch to J, and then I got, anyway. So this is the equation that has the most consequence. These two are just brought along as the two constraints of the system. So if I solve the first equation for nj, no problem, I can do that. That just gives me this function here. Okay, I'll let you examine that and make sure that that's the solution for this ni, that you can actually do that. Notice ni only appears in this location here. It's canceled out in the other locations. So how do I do that? I would take the inverse of the log function, that's the exponential function, and I get this. But this has two Lagrange multipliers in there. I can get rid of exactly one Lagrange multiplier by using this constraint right here. Okay, so I know that if I sum nj from j equals 1 up to r, I have to get exactly n. So if I do that, I can then solve for the alpha parameter. It's going to still be in terms of beta, but at least I can get rid of the alpha in terms of beta. All right, so if I do that, I get this whole term here, I guess. And I want to get rid of that because it has an alpha in it. And now I could solve for alpha directly, but solving for the exponential of alpha plus k Boltzmann over k Boltzmann, getting rid of that, that's enough. Okay, so that tells me that when I normalize things, I should get this value here. Okay, so I'm going to let you go through the arithmetic of that. It's not difficult. All that I'm doing here is I'm solving from this equation, and then I'm normalizing using my constraint. Okay, just the mass constraint. That gets rid of the alpha parameter, but I still have everything in terms of beta. I can't get rid of beta so easily. I'm going to show you how to get rid of beta in the next lecture. So that gives me this. Okay, this is the so-called partition function. That's going to be very important, it turns out, for our analysis. But okay, so this gives us kind of like a partial answer. We haven't been able to get rid of the beta. So to determine beta, we're going to have to use the other constraint of the system. What's the other constraint of the system? That is the energy constraint. So I need to be able to sum up these quantities, right? Using the energy constraint here. So multiply each ni by ui and sum from I equals 1 to r. That value has to be equal to u, that total value. And that's exactly what I've written here. So I claim that doing this allows you to find out what beta is. Okay, doing this allows you to uniquely find out what beta is. But the problem is that's a complicated proof and it's a complicated calculation. So what I'm going to do instead is, so first of all, I'm simply going to claim that beta is uniquely determinable by this equation here. But I'm going to show you three examples and then show you through a theorem later how this is actually done. But notice that if you stop short and you believe what I've said there, that claim that I made, that beta is uniquely determined by the parameters in the system, then we're done. We've already solved the problem at least to the point that we wanted to. We've characterized the equilibrium values for this macro state. Okay, each to find the equilibrium, we've simply found these numbers. I'm going to try to motivate and tell you what these numbers mean, okay, momentarily. It's written in terms of this important function called the partition function, which is a mysterious function that plays an oversized role in statistical mechanics. The beta is still undetermined, but I'm going to try to show you and convince you later through semi-rigorous mathematics that beta is equal to 1 over the temperature function. So if you believe that, we're done with this theorem. So in lieu of a proof of the last claim, I can show you through a couple of examples. We're going to do one today, and then we're going to do the next one in the next lecture on Thursday. I'm going to show you that this beta will only depend on the total internal energy and the total number of particles n, and is in fact related to the temperature. All right, the way I can do this is through an example, at least to begin with, and that's where we always want to start. And now I want to say about the beta function and its connection to the temperature. In the physics literature, this is done, in my opinion, very, very poorly. And I had to read this 100 times to figure out exactly what they were doing. And now I think I've got a more or less semi-rigorous way of doing this. But an example will show you the track that I'm on and my thinking in this setting. So let's consider the following two-state system. U1 is equal to 0, so that's easy. And U2 is equal to some small, well, it doesn't have to be small, just some positive number epsilon. Okay, so the constraints are we have a fixed number of particles n and a fixed total energy u. If you tell me right away that the energy levels are u equals 0 and u equals epsilon, again, epsilon is positive, not necessarily small, then what do we have here? Well, I know that my two states have to sum up to n, and I also have two states which have to give the fixed energy budget. I have two equations and two unknowns. Actually, there's no equilibrium here to find because I can uniquely solve for n1 and n2 for this system. I can uniquely determine them. For example, the solution for this for the system, I can solve first for n2. N2 is clearly going to be u over epsilon, and therefore I can substitute that back into this equation and find out what n1 should be. So there's no maximizing the entropy in this case. I can simply determine the energies directly from these two constraints. So is that violating our postulate? The answer is no. It's not violating our postulate. It's just saying that if you have a two-state system, then the mass and energy constraints already constrain it enough that there's no degrees of freedom left. Its entropy simply is it's the Gibbs entropy of that system, okay, that macro state that you just found above. Now, there can be a lot of microstates represented that macro state, remember? But we've fully characterized at least the macro state. The Gibbs entropy is something which is easy to calculate. It's just going to be the sum of these two quantities here. And that's because I know the values here, and the Gibbs entropy says that once you know those values, you plug them into this formula and you get the entropy. There's no maximization that needs to happen. Okay, there are no free parameters and no maximization. We've the two constraints uniquely determines the system. Now, for the entropy at equilibrium, we're going to come up with a very special name. So keep in mind that we only talked about the entropy for equilibrium systems in thermodynamics. In the statistical basis for entropy, the entropy is defined even for non-equilibrium systems. Okay, if you tell me what the state is that you want to examine, I can tell you what the entropy is for that particular macro state. But whenever we find the equilibrium macro state and plug that back into the energy, we're going to give that a special name. That's going to be called the equilibrium entropy. Plug the equilibrium macro state back into the Gibbs energy, and that's going to give us the equilibrium function for the entropy. We're going to show that it's only a function of two variables, u and n. And in fact, we're going to show that it's going to be a homogeneous of degree 1 function. So let's calculate the temperature using that procedure if we agree that this is the equilibrium entropy. In fact, that's how we define it. So how would the temperature be computed from the thermodynamic point of view if we knew what the equilibrium entropy was? Well, this is easy too for us. Once we know a bit about thermodynamics, it's just going to be 1 over the temperature equal to the derivative of the equilibrium energy with respect to the change in energy. Okay, so we're just going to take the derivative of this function, whatever the heck it is, with respect to the energy. Well, I have that function. It's given right here. And notice already I can see it's only a function of n and u. Okay, remember epsilon, this energy level, is fixed for us. So I can take the derivative with respect to u of that function. And if you do that and you simplify, I'm not going to do this live. I'm just going to ask you to do this. You can get this function right here. Okay. And you notice that the temperature, once I invert things, is now also a function of n and u, as you would expect. Now, let's go through and do something slightly different. Let's use our equations and our general solution procedure that we developed in Theorem 9.9 and do the same thing and see if we can eliminate beta in this case. So put this in your pocket for a minute. 1 over t is equal to k Boltzmann over epsilon log of this quantity here. This quantity in here has to be a unitless number, which it is nicely. And it has to have ultimately units of 1 over temperature, which according to this constant is true. Put this in your pocket for a minute. So I can go through the general procedure for equilibrium from Theorem 9.9 that told us what the numbers n1 and n2 should be equal to. Okay, so I'm just going to use that prescription. Remember, it's some complicated formula involving n, the partition function on the bottom, an exponential of a function on the top. So if you work out the numbers, that gives me exactly these two distributions for n1 and n2. n1 and n2 at equilibrium are those distributions. The energy constraint, that, as you can recall, was just equal to this, and we see that this comes out nicely and very beautifully, right? So we have to be able to show that n2, which is, we know u over epsilon is equal to that. So we can solve, therefore, so because of this energy constraint, okay, well, here's the general energy constraint, we can solve for beta in this case. And if we do that, I'm going to let you check the details of this, we get this function here. So now go back up and check what we had for 1 over temperature before. That function. If I use the energy constraint and the procedure from Theorem 9.9, I can solve for beta exactly. And in this case, what I find is the exact same function. So in this case, at least in this case, we see that beta is equal to 1 over the temperature. So What I want to show you with general calculations later on, this is always, always, always the case. That if I define the temperature through this procedure right here, okay, there's two steps. The equilibrium entropy is defined as the Gibbs entropy at the equilibrium value of the macro state. Okay, so that gives us the equilibrium entropy. We use the thermodynamic definition of temperature. 1 over T is equal to the derivative of the equilibrium entropy with respect to U. That gives you some function, and I can always show you that beta is exactly equal to 1 over the temperature, that same function. So we're going to see this is generally true. Beta is equal to 1 over the temperature. This allows us to go through and replace that weird Lagrange multiplier that appeared on the scene with 1 over the temperature in each of its locations. Okay, so I'm going to stop there, and I'm going to reinforce this idea with another example and then a more rigorous calculation coming in the next class. I went through a lot of notes very quickly, so what I do want you to do, I encourage you to do this. Please go through these notes and read through the details that we didn't cover in class. Go through those details, go through those concepts, and make sure you understand them, because I know I did move a little bit quickly today. But with that, I'm going to stop and I will take your questions.